begin today's class. So what are we going to talk about today is we'll be talking about learning a representation. Because this is one of the, I think, turning points in research on machine learning. And I kind of introduced this point already. So what we will be doing is we'll be trying to think how to automatically learn representation of objects or of contents that we are going to analyze. And this is in opposition to this classical machine learning, where this representation was derived based on some criteria that were thought to be correct. And it appeared that in confrontation with real world data, it appeared that these criteria are never complete or never sufficient. So what is representation learning? And this is, we have some objects, image objects, we have some faces. And what we would like to accomplish is because in any machine learning, sooner or later, we need to transform this information to some quantitative description, to some vectors. And what these vectors should contain, they should contain information that is relevant for the task. If I'm talking about classification or recognition, what is relevant is to extract all properties that are useful in discriminating between objects of different classes. So this is relevant for the task of recognition. And how can we approach this idea of learning this representation? How to learn this representation? If I would like to have a good representation of objects like faces, I know that to recognize that there is a face, it's probably necessary to recognize pieces of this face, and the pieces are eyes, or is a nose and mouth, and maybe some other elements. So basically, these components of a structure, they are some characteristic points or characteristic regions that we most likely use in recognizing objects. So the first thing is we would like to be able to transform input raw data in such a way that there is an information about these individual components provided in this X vector. So when I will be transforming this image, this raw image, into a vector, there will be a vector of features or of properties. I would like this vector to contain some information on the presence of these characteristic points, like this eye-like structure is here represented, or maybe somewhere there will be represented a mouth-like structure, and more. So that's the first thing. The first thing is try to be able to detect presence of some particular structures, local structures, most likely. And the second element, so I would just summarize this as answering the question on what is present, what structures are present in input. And the second thing that is, I think, quite intuitive if we are talking about recognition is what are the relations between these components? So how they are mutually spatially related? What's uh, uh, relation between locations of these characteristic points? So this is what I would like to accomplish. A good representation would be a representation that informs me about everything that is really important when I'm analyzing an object. We are talking about images right now, just because images was a domain of the first success of deep learning and this concept, this representation learning concept. So the first thing that I would like this representation to be able to capture is this structure of these characteristic points. And the second thing that I wish it to capture is information about spatial relations between these characteristic points. And there is more. There are more requirements for a good representation. So what are other requirements for a good representation? It should be invariant to different possible transformations that can occur to objects. So, for example, if I have an image with this face, and I have another image, so there is one image with the face here, and another image is with the face here. This is exactly the same contents. The only difference is translation. So good representation should be invariant to this transformation. It means to translation. It should be it should feature, or it should possess an invariance to a translation. So translational invariance. This is one of the fundamental properties of the good representation. But more, if I see the same face, but the person is in a different distance from a camera, I'm changing a scale. So another thing that is required is scale invariance. What else? Person might change a pose. That means a pose in 3D. In 2D, we can say this is a rotation. In 3D, it is a pose change. So it should also be pose invariant, or invariance. It should provide pose invariance. So there are several requirements for a good representation, and real world is full of different exceptions. So all attempts that were made previously to find a good idea for representation derivation just failed. They were okay, but they have never been better than humans. So this concept of representation learning emerged, and it appeared to be very successful. How can we approach? Because we would like to learn this representation. And basically, what learning means? Learning means that I will have some parametric function that transforms my input. So learning means that I need some parametric transformation. Parametric transformation. So this parametric transformation basically contains this vector of parameters. And learning means actually trying to find better parameters based on examples. So I would like to design some idea for transforming input to the output, and this idea should provide me with satisfaction of all these requirements. So these requirements are very challenging. I need to be able to recognize different local structures. I need to be able to represent relations between these local structures. And all of these should be invariant to typical changes that can occur to objects. So what could be a candidate for such a parametric transformation? That's can give us some hope for satisfying this all of these requirements. Let's consider one-dimensional example, because this is simpler. It's simpler to handle. So let's assume that we have a structure that is, let's say, is an eye, is part of an eye, but I'm talking about an eye kind of in one dimension. So so I can say that this might be a line of my image, and somewhere here I will have a distribution of values that are characteristic to an eye. So let's assume that this is just for simplicity, that this is a binary image. So I can say, for example, I have here 1, here 0, here 1. So 0 is a pupil, is dark, and it's surrounded by white regions. And if I would like to search for an eye, how could I do it mathematically? Basically, I'm looking for a pattern. So for some pattern of values. And this example must be, it needs to be simple. So let's assume that this is just a 3-element pattern, but obviously it can be a much more complex pattern. So how can I detect presence of this pattern? Well, something that is nothing really very innovative, because we are talking about this kind of analysis. And for example, what I can do is I can compute a dot product of this piece of my input data with some other vector that is, for example, arranged this way: 1, -1, 1. And as you see, if I design my vector, this vector I will call a filter. So I can say that this is some vector h. And this vector h is just a vector that is composed of 3 entries. And if I compute a dot product, so if this is, let's assume that this is a column vector. So now I'm transposing this. So if I want to say how similar is this vector to this part of my image, one-dimensional image, I can say that I can measure it by computing a dot product. So H transposed times, and let's say that this is some position I. So this will be my, I will call it X. This is an input vector. X here is an input. This is not a representation. This is just an input. So I can say this is X, and I will put a little superscript I, means that I am centering my H at a position I. And the result will be a value. This is a yi. A dot product is something that is evaluating similarity. And in this case, I'm evaluating a similarity between 3-element vectors. And the fact that I'm using this particular vector is because I have knowledge that I'm I'm looking for this kind of structures. So if I would like to make detections of some particular structure, I should provide a filter that is specifically derived to detect these structures. And for this particular structure, I can say, what is the right filter for doing this? And observe that for any, assuming that this is a binary vector, the maximum response that I will get, it means the maximum value of a dot product, will be for this particular structure. This is the maximum one. Any other structure will give me a lower output or outcome because it does not fit that well to my structure, because I'm encoding a structure that I am looking for in this filter. So I can say that the filter, it kind of encodes a structure. So this is a role of this filter. This filter encodes a structure. So this is a very simple, but this is the first very important point, that I can try to search for different structures by using filters. That these filters, they provide me with kind of a prototype of a structure that I am looking for. So I'm looking for a structure that is encoded by this filter. The thing is that I won't know exactly the entries of this filter, because this is what I will be learning. This filter will have, for example, 3 components. So basically, this will be something that is a parametric transformation. So this will be something that I will be trying to learn. I will be showing pictures or images, and I will be trying to tweak these parameters, to change these parameters of the filter so that I get the best possible discrimination or recognition or classification. I will be learning this representation. I will be learning this filter, but what I will learn something that is sensitive to a particular structure. So the idea for searching for this transformation of raw data into representation is rooted at properties of a dot product. A dot product is a way for extracting some particular distributions or structures from input data. And the second thing is, if I have this one-dimensional image, I have no idea what happened. Okay, so if I have this one-dimensional image, it may contain my structure in several different places. So this structure could be here, but it also could be here, and could be obviously in some other line of my image. So if I would like to detect something, regardless of where it is located, so it means if I would like to detect a structure and have this the translational invariance, what I need to do is I should apply the same filter here. So this will be this filter minus 1, 1 plus 1 minus 1 plus 1. And here should be exactly the same. So I need to use the same filter for transforming this input vector of data. if I am looking for a particular structure, I have to assume that this structure could be anywhere. So what I was doing before is I was computing a dot product. So that was a dot product that was a detector of a structure encoded by a filter. And now what I can say is that if I would like to apply the same filter to this whole row of inputs, then at ith output, this is some particular output, let's make it I. So this is there will be a result of transformation, will be this yi. So this result of this transformation will be just a dot product. And what is a dot product? A dot product is a sum of products. And this is a sum of products of what? The first thing, the first component will be an entry of a filter. The second component will be an entry of an input. So if input is X, I will have and I will have entries. If my entries, let's say that this is my filter, and I will now label its entries as this is a -1 entry, this is 0 entry, this is 1 entry. So these are labels. So these labels, I say that they are denoted with K from, let's say, -1 through 1. And what I'm computing is I'm computing products of corresponding entries of a filter and of an input. So this is mathematically, if I would like to say, what will be a result of this dot product. So if this is a, let's say, a position, if I is a position number 7, so what I will be doing is I will be computing x6 times h minus 1 plus x7 times h0 plus x8 times h1. Yes, this is I'm specific right now. This is a general formula, and below is what if I'm interested in the output number 7, or what will happen if I place my filter at around the position 7. So this is what I get. So a result of my operation. So if this is my input vector, this is my x, and if I apply this filter h, so if I will be sliding this filter from the first position to the last position, and I will be computing the output, what I will get is I will get an output vector. So this will be an output vector y. I can say that this output vector y, it will be composed of these values. y1, there will be yi, and will be some last element, y something. And each of these entries will be computed this way. And I have a name for this operation, and this operation is the operation that I will name as a correlation of these two functions. So correlation is just aggregation of dot products. And each dot product applies the same arguments, but they are shifted with each other by 1, because I'm applying one vector at different positions of the second vector. So this is a correlation. So this is something that is an extremely important term in data processing, data analysis. And correlation is kind of a global operation. This is a collection of dot products. So dot product is at the core of correlation. And the correlation is an operation that we have two vectors. These are arguments, and a result is also a vector. So this is an operation that transforms vectors into a vector. If I make a very simple modification, so let's assume that my filter or my vector H is a vector that is composed of three numbers, A, B, and C. If I flip it, so if I produce a vector CBA, I can say that exactly the same result I will exactly the same result I can get if I will be using a formula that is just slightly modified with respect to the previous one. So it's identical. The result is identical. So if I'm taking k equals -1, then I am applying the rightmost element of input vector by the leftmost element of the filter. So it's equivalent. So this line and this line and this line are equivalent. But the name, this operation has a different name. This operation has a name that I'm sure you have heard already. It's a convolution. So convolution, again, it's exactly the same as correlation if we flip a filter. So a convolution will be an operation, again, that transforms two vectors, and frequently convolution is being denoted with this asterisk. And this is an operation that is exactly the same as I explained. It also involves dot products. The only difference with correlation is that prior to this operation, I'm flipping the filter, and it transforms, just like correlation, vectors onto a vector. So just to summarize what I have said so far, I can detect some structure that is present in an input row or one-dimensional information if I apply a filter, and if I will be computing dot products, and as I will be interested in the same structure along the whole one-dimensional data, I will be applying the same filter at each position of my input vector. And I can say that I am performing an operation of either correlation or convolution. Convolution is something that is preferred over correlation, although it sounds or looks weird a little bit, because I don't know whether you have heard about signal transforms or transformations using Fourier basis function set, or I'm pretty sure you have heard about Fourier transform or discrete Fourier transform. And one of the purposes of transforming data or signals using Fourier transform was that the filtering instead of these dot products, we could replace this operation with multiplication of the results of this transformation. And it was directly equivalent to convolution, not to correlation. That's why convolution was the method of choice when we are talking about signal transformations. But basically, they are both equivalent if we just make an appropriate flip of a filter. So what we have is we have some idea on how to extract some particular structures from input data. And if I know what structure to search for, I can just propose a filter. If I do not know what is really interesting, what is important, then I will be trying to learn this filter. Just a few more things about convolution or correlation. Let's assume that we have, again, we have input. So this is an input vector x. And let's assume that we have a filter. So this filter is, let's assume it is a 3-element filter. Observe that if I would like to transform this input into the output, if I would like to tell what will be at the output of at the first location, what will be a value of, let's say, y0, what I need to know, y0 will be a result of a dot product. So this will be x minus 1 times h minus 1 plus x0 times h0 plus x1 h1. The obvious problem is that I don't know this element. And the same applies to the last element of my correlation or convolution. What is the, I'm sorry, let's make it better. So if I would like to place this filter here, center it around the last position. So if I had, what will be yn, for example? Again, I won't know this element. This is something I don't know. So if you, it's quite obvious that if I would like to use an actual information that is inside my input vector, then my result of convolution, if my input vector is a vector that let's assume has n elements, then, and so maybe this is the size of my input vector. Let's make it a row, just not to cause confusion. So I have a row vector, and it has, this is one row and n columns, n elements, and also I have a filter. So my filter, it's assumed that it has 2r plus 1 elements. The filter, a reasonable thing is that it should be symmetric. So it should have an odd number of elements, like 3 elements or 5 elements, because I would like to center it at some location. So I would like my left and right tails to have exactly the same length. So it is very often the size is encoded using such an expression. So if this lowercase r is 1, that means it has 3 elements. If r is 2, it has 5 elements. So if I have this particular input and filter, then I can easily conclude that my output, so this is my output vector, will be a vector that cannot be that long if I would like it to be computed using information that is embedded in X. So it will be a vector that has a size n minus 2 times r. So if r is 1, it will have just n minus 2. So you see that if I would like my output to contain only true values, actual values that result from information that is in X, then a size of a result will be smaller. But what I can do, if I would like the the size of my output vector to be also 1 over n, what I could do is I could extend my x vector. So my x vector could be extended. For example, by adding, if my r equals 1, I can just add one dummy value at the beginning and at the end. And I'm saying that I'm doing a padding. So this is padding. So if I would like my output vector to be exactly of the same size as input vector, I have to do padding. And padding is the term that is commonly, that will be frequently met in our further considerations. So that's the first thing. And then output vector, a result of a convolution, has exactly the same as the input. What else can I do? Another term. What else can I do here? I can apply my filter. And so this is my X. And what I can do here is I can Can you hear me right now? I'm sorry. What was? I wonder when it stopped. At which point the connection was broken. Okay, so this padding is okay. Y is not the same dimension as x, because, so once again, if I am applying a filter, so let's make it black. So if I apply my filter, this is my x, this is my x, and this is my filter. So if I apply it at a position number 2, and these are positions, this is position 1, this is position 2, this is position 3. So if I center it around number 2, a cell number 2, then I can compute the output y2, because I have all information that is necessary to compute the output, because this will be h1 times x1 times h minus 1 plus x2 times h0 plus x3 times h1. And here are indices of filter. So this is my filter. But if I would like to center it or compute a result for a location 1, I would have to center my filter here and observe that I don't have this value here. So the recording is still working. The recording is still working. So if I would like to compute what will be y1, as you see here, let's make it red. As you see, it is missing. The first product is missing, because the first product is x0 times h minus 1, but I don't have x0. So because of that, I might be interested only in results that are meaningful, that are correct. Correct results are results that I have all data to compute. So my outputs, in this case, if I would like to rely only on information that is available, my outputs will be only from y2 through yn minus 1, because this result and this result are unreliable. I hope that's clear. So if I would like it to have the same dimension, then I will need to do this padding. And this padding is to just place here something, but it will be artificially placed. What typically we are placing? Typically, we are placing zeros, but you can also place something that is a copy of the neighboring element. So that's another idea for padding. Now, let's move to the other aspect. The other aspect is something that I started to introduce here, but let me say it again, because connection broke. So what is another possibility or another aspect of computing this dot products between inputs and filters? The other aspect is, for example, I can say that I can compute the output at the second position. And then, instead of moving this filter by 1, let's move it by 2. If I move it by 2, that was my initial location of my filter. But now I will center it here. So the second location of my filter will be like this. So this is my second location, and I compute y4. And I can move it again, not by 1, but by 2. And I can compute y6. And this is absolutely justified because I'm using all information encoded in input data. Observe that I'm not missing any data because there is an overlap. All the time, there is an overlap between filters. There is no any information left without being taken care of filtering. And as this is possible and legal, and it produces results that are meaningful, it is also used in I can compute these convolutions if I am if I am moving a filter, not one by one, but using some bigger steps, I'm saying that I'm applying a stride. A stride is just this shift between consecutive filter locations. So if in the next step I am moving my filter by 1 and computing convolutions, so this is the scenario that I considered previously. I can say that my stride here was 1, but now there is another scenario where I am moving my filters. So it was initially at this location, but then I moved it not by 1, but I moved it by 2. So I placed it like this. And in the consecutive step again, I moved it by 2. So I'm saying that now my stride is 2. And I can change this stride as long I can increase this stride as long as I'm not starting to lose information. And when I will start losing information, if my filters will be placed too far, so that there is a space, a portion of an input data that is not covered by these computations. As long as I'm not losing this information, it is legal. So that's another parameter that will be used to characterize convolutions. So padding and stride will be parameters that are used to clarify exactly how am I performing my convolutions. So these are two notions that are, I hope, clear to you. So we have and one more thing just to conclude. Observe that if I am using a stride of the size 2, of a value 2, then my output filter will have a size that is twice lower, because I will have every second element of input vector covered. So as you see, introducing a stride that is larger than 1 can somehow it is just compressing me output values, output data, or it is reducing a size of the output resulting vector. And why is it interesting? Because let's assume that I have I'm searching for these eyes or for an eye. I'm searching for an eye, and for example, so I had a filter, and this filter was designed to detect an eye, and I found it here, and I found it here. What does it mean? It means that here these values are large. So I have a large value of the result of this filtering. What will be a large value? For example, 2. So for the for a binary image, and this filter 1 minus 1 1, if I find this structure that corresponds to an eye, and I assume that this is this structure, I will get a result 2. But these results now, if I have a stride of 2, and for example, this is the output number, let's say 8, and this is the number 8, 10. Observe that these outputs become neighbors in my output representation. So these are neighbors. So if I would like to ask, maybe there are 2 eyes next to each other, answering this question will be trying to make a convolution that contains this kind of a structure, for example, or let's say something like this. This is, I've made it up. But if there was an eye at 8 and there was an eye at 10, there will be a large value of a convolution with this filter. There will be a large value. So means that if I operate at the output of my first convolution, and this output has a reduced value, I can say that I'm operating at a different scale. I'm operating at a different scale, and at this different scale, what I can do is I can start combining features that I identified in this first scale, in this original scale. So changing a scale is getting to a more general way of analyzing input. We will be back to this, but I'm just indicating that there is a close relation between this idea of reducing, of using a bigger stride, which reduces a size of an information, and it is related to changing a level of analysis. At this more, I have a more general level of analysis now. I have information that is being somehow compressed, and on that compressed information, now I can look patterns on that level, and I can go further. Okay, so I will be back to that again. So just to conclude right now is we are done with introducing a convolution. So I will have an image, or I will have any data. Let's say we are talking about about vectors. So I have some input vector x, and I have some filter h. So now I will draw it in a different order, and as a result of that, so this will be some block that produces me a result of this convolution. So this will be y. If I have a filter h1, this will be y1. But obviously, if I apply a different filter to this, so I have a different filter right now, h2, the same input, obviously the outputs will be different. So there will be outputs will be different. So what I can do is I can use many different filters, and each filter will be trying to detect a different property of this input data. And each of these filters, H1, H2, and so forth, I will be trying to learn. I will be trying to learn these filters. What should be their values to get the best classification results? And all of these filters, they operate on input, on the same input. So I will be saying that all of these filters, they belong to the same layer. So I will assume that an architecture of my network will be the following, or of my structure will be the following. I will have an input, and this input will get filtered. So I'm changing a little bit right now. Maybe I will use a different color. So I will have a kind of a set of filters, and I will be converting this input into a set of output vectors. So these will be vectors that are results of analysis performed with different filters, H1, H2, H3, and so forth. So right now, this is an architecture that I'm considering. It's right now. I will say that all these filters they form something that I will call a convolutional layer. Convolutional layer. So this is the first kind of a step, or the first part of processing of input. I will have several different filters. Each of these filters will extract some other information from input and will produce vectors Y that are transformed inputs. And these transformed inputs, they will contain information whether some particular pattern is present or not. And this will be encoded by a number, by a value. And this value will be a result of a dot product that I am performing between a filter and each position, each location in input image. So at the basis of all of these operations is this dot product. So dot product is what I'm computing is I'm computing a dot product of a filter and a part of input centered at I. And the output is just an element of the output vector. And observe that basically it is a transformation that just a linear neuron is doing. Because a linear neuron is an element that, if my input is just this portion of input vector centered at I, and my weights are identical to a filter, then what I'm doing is in a linear neuron, so I'm sorry, YI, a linear neuron is something that just is computing me the following expression. So basically, convolution can be performed by a collection of neurons. So once again, if this is my input, or let's make it again input vector. So this is my input vector. So convolutions can be computed using neurons that are located with some stride, either 1 or 2, or depends on what is the size of this filter. And the result of this convolution are just outputs of my neurons. And what is important is that each neuron here has the same set of weights. So all weights, unlike in a structure that we were talking about previously, this time every neuron will have the same set of weights. So we can visualize it this way. So basically, the weights are these filters. So these are equivalent to a filter. So when I will be trying to learn a filter, basically I will be trying to learn weights of neurons. And if I would like to learn weights of neurons, basically I will be doing something that we already know. When I'm training or when I'm training my neural network, I know that weights of a neuron are being learned or corrected by applying this delta rule. Delta rule says that if I know the error that the neuron makes, so this is an error of this neuron, and I know what is a nonlinearity, and I know what is the input, I know how to correct a weight. So this is x, not y, this is x. And now I have a linear neuron. So this derivative is just a constant value. So for a linear neuron, this is constant. So what I can say is that my weight update for a linear neuron is proportional to this error that is back propagated and input. So we are closing to the point, to the moment when I will be able to present you with a rule for training this convolutional layer. Because this is something that is crucial. This is most fundamental. I at the beginning, I just qualitatively introduced you with the concept that if I would like to learn a representation, I can use a convolution as a transformation of input into some representation that is meaningful because it captures characteristic patterns that occur for my input data. And the most important element to capture the right information is to use right filters. And these right filters are just weights of neurons, because filtering or convolution is equivalent with applying a layer of linear neurons. Each neuron has exactly the same weights to process input information. And now the point is how to find these weights, because I don't know it. I don't know the filters that are good for solving a particular problem. And that's why I will try to learn it. And what is learning? Learning is application of pairs that include input sample and target. So the learning is I'm applying a sample, I'm computing a loss, and then based on this loss, I will be trying to compute updates of my parameters. So basically this is learning. And now I have a delta rule, and I have backpropagation algorithm. That the most important finding from this backpropagation algorithm is that even if a neuron is very deep in a structure and I don't know immediately what is its error, I can determine its error. And this determining of the error was basically something that was a derivative of this loss with respect to a particular neuron that I'm interested in, or the output of this neuron, times a derivative of this output with respect to this parameter that I'm interested in. I'm interested in this parameter, so that was a general formula for a delta rule in this complex structure, and this was just this error, this propagated error. That was this propagated error. So this is exactly the same as here. So basically, this is exactly the same formula, but in this formula, I'm just explicitly trying to identify this error as a derivative. As a derivative of loss with respect to the output of this particular guy. This particular neuron has an output y. And it is an element of a larger network. So basically, my neuron that I'm interested in, this will be a neuron that I will be interested in. It will be in this layer. These are these neurons. I'm interested in this neuron. So I have some neuron that is at the location P. So this will be YP. And there will be another neuron that is at the location Q. So there will be YQ. There will be another neuron at the location R, and so forth. There will be more neurons. And I am interested in trying to figure out what should be an update to a weight, let's say -1, because my weight vector, let's assume that this is a 3-element weight vector, W-1, W0, W1. It's a filter because these are linear neurons, but now I'm using a letter W instead of H. So maybe I will just indicate that this is a weight number -1, but this is the same weight because all neurons have exactly the same weights. It's not like in a multiple layer perceptron where every neuron was an individual. Now, all neurons here will be, these are these neurons from this layer. All neurons have the same weights. So what I would like to do is I would like to find out what will be an update to this weight. What will be an update to this weight? If you look at this formula, this general formula that applies to these multiple layer structures, you will notice that the error or the loss attributed to a particular neuron is just a derivative, or the error that is attributed to a particular neuron is just a derivative of a loss with respect to its output. But now you see that if my weight -1 is wrong, there will be several components of the error. That's the weight W-1 will affect my loss through multiple different paths. So what I can say is that basically, if I would like to tell what will be the error that is caused by inappropriate value of a weight W-1, I will need to say that basically this will be an expression that contains several components. This will be YP times YP with respect to W-1. And this will be an element of a sum that applies to all of these neurons, that each of these neurons is contributing with an error if this weight is incorrect. So there will be YQ with respect to a derivative of YQ with respect W-1. There will be, again, next term that is related to an erroneous value of the weight, but now for the neuron R, and so forth. So what can I say if I would like to know what is a derivative of an error with respect to a particular weight? I will get such a sum. For an individual neuron, I just had a one term. If a neuron was individual, this weight of this individual neuron was unrelated to other neurons. It was just a parameter of this particular value, of this particular element. I'm sorry. But now, if I would like to know what is a derivative of a loss with respect to a particular weight, you see that this will be a composition of different terms. And each of these terms, basically, this is this error that I'm projecting onto a neuron P. And this is an error that I'm back projecting onto a neuron Q. And this is an error that I'm back projecting to a neuron R. So what I have is first, I have an error projected to an output of a neuron. And what I have here, I have a derivative of my output with respect to the weight W minus 1. So here is a derivative of my output P with respect to a value minus 1. And basically, this will be an input P minus 1. And here, this is just an input Q minus 1. And this is an input R minus 1. So if I would be interested in computing a derivative, an update of the weight 0, this is the central one, I will have an expression that looks like this. There will be delta P, an error that is projected on the output of the neuron P. Here is an error projected to an output of a neuron Q, and the same with the neuron R. And here will be just XP, because this weight W0 is a weight that connects my input X. If this is a position I, this is an input I, and this is a weight W0. And here was output Y, and here was a weight W minus 1. So it was Xi minus 1. So in the second case that I'm just drawing, it will be XQ, and here will be XR. And if I would like to know what will be an update of my weight 1, will be, again, the same P remains, the same delta remain. So there will be, this is just the same error, but now I have different inputs. This is P plus 1, this is XQ plus 1, and this is XR plus 1. So if you look at these expressions, you will see that my update will be something that is, here is a dot product between an error vector and a vector of inputs that is shifted by 1 to the left, or the vector that X that is all moved one element leftwards. Now here is a dot product between the same delta and just a vector of inputs. And here is a dot product of an error vector and inputs that are one element to the right. So the first observation is that an update will be composed of several components and update, or of several updates. And each of these updates basically is a dot product. And each dot product, so the first dot product that relates to the first weight is a dot product that I'm performing, is a dot product. So if I have a delta, this is a delta, let's say this is a delta vector, I'm propagating information about a loss, about an error downwards. So these are just propagated errors at the outputs of these neurons, that form my filter. And here I have a vector of inputs. This is a vector of inputs. This is an x vector. So this is a vector delta, and this is a vector x. And what I'm doing, if I want to compute an update of my central element of my filter H or my filter W, these are equivalent. If I'm interested in computing this central element, or W0, or an update of this W0, what I'm doing is I'm just performing this dot product. If I want to compute this weight update, so if I'm computing a delta or an update of -1 weight, what I'm doing is I am kind of shifting the whole vector by 1, because now my weight takes care, is interested, my -1 weight of some location I is interested in what is going on at input x -1. So I can say that basically I can do it exactly if I multiply or compute a dot product of errors, projected errors, and input shifted to the right. If I'm interested in the last update, then I'm interested in this, in xi plus 1. And here is my delta. Here again is my delta. It comes from the top. So in this last case, this is as if I'm producing a dot product, but now of an x vector shifted to the left. So basically what I'm doing here is I'm saying that my update is a convolution between two vectors, delta and x. So that's the most important conclusion of the analysis, that tells us how to update weights in this layer of these neurons. So the training looks in the following. I have a sample. This is a training sample where I have input and target. So I have input, and I apply this input xi, and first I propagate it, but now in my first layer I will have neurons which have exactly the same weight vectors. So this will be my every neuron here. I will make them blue because they are all the same, and they have W1 vectors, and there will be something atop of them, many layers. I'm not so far, I haven't got so far, but imagine that there are many layers, and at some point here there will be output of my whole network. My whole network will have m neurons, for example, and this will be an output of this network. And here I will be confronting targets. Target will be here a vector. I'm confronting a target and these outputs of the whole network, and this will give me just the loss. There will be a loss, and I start propagating the errors using backpropagation algorithm. And I will at some point get here. So I will be able to identify what are individual errors that are performed by neurons of this first convolutional layer. And if I learn these neurons, this will be this vector delta. Then, since I know xi, I know this, I can tell what should be the update to weights of this first layer neuron network weights. So, and again, everything is within the same framework of backpropagation. A difference is that every neuron in this layer has exactly the same set of weights. And therefore, I will be making an update that is kind of based on performance of all of these neurons. And this update is just a convolution. So this is basically this update. This is the update that I will be doing for these neurons. So this is what I will be computing. I hope this is clear. It's nothing that you will be asked to implement on your own, but if you are asked to do so, this is nothing different than backpropagation. The only difference is that now all neurons in this layer are the same. And since all these neurons are the same, the update is computed in a little bit different way. This is not a delta rule, but this is something that involves this convolution, because I have a distributed influence of a weight that I'm correcting. And this distributed influence is captured by a dot product between errors that make all these neurons and input that is appropriately shifted. And I can summarize it in using a convolution. So it is nothing different than backpropagation in principle. And there is a difference in detail because I will be correcting weights to all of these neurons at the same time. Just at the end of today's meeting, I would again go to some qualitative analysis. So I will return to that. So that you will have an opportunity to maybe think over this concept again and again. The thing that I would like to introduce at the very end is a two-dimensional convolution. So I have a one-dimensional. What I was doing, I was just presenting an example where my input information was one-dimensional, but the whole concept has been introduced based on images, for images. So images are two-dimensional. So if I would like to find a structure in 2D, so this is an image, some width, some height, and there is a structure here. And how could I detect this structure? I could detect this structure by applying a two-dimensional filter. So now the filter will be two-dimensional instead of one-dimensional. And basically, it will analyze points in a two-dimensional region. So I will be analyzing information in the input, and I will be producing the output. But this time, everything is two-dimensional. So my output yi will be a dot product, but this dot product is a dot product that involves two dimensions. So there will be some k from minus r, and there will be some l from minus r to r, and there will be input image that will be composed of entries x, and here will be a minus chi and j minus l times, and here will be my filter k l. So I will have my filter h now is a structure that, for example, is a 3x3 structure, which has entries minus 1, minus 1, minus 1, 0, minus 1, 1, and so forth. Here will be 0, minus 1, 0, 0. There will be 0, 1, and there will be 1, minus 1, 1, 0, and 1, 1. So this will be my filter, and my image will be an array of values. And I will use a two-dimensional convolution. That means this is just a single output, and if I now you see that I will be moving this filter using, for example, stride 1 along x and along y, or along width and along height, and I will be producing an output. Now this will be a matrix, and the output of this matrix will be just a result of a convolution of input matrix and a filter. So now we have two-dimensional data, and everything that I told for one-dimensional convolution applies here as well. For example, if I don't use padding, my y, my output array, output matrix, will have a smaller dimension than my input. If I would like to make it the same, then I need to use padding. The second thing is I can use a stride. That means I can produce output that will have a reduced size. For example, by 2 in horizontal direction and by 2 in vertical direction if my stride will be the same and equal to along both axes. And if I would like to process an image, let's assume that I have input image. This is my input image, and it contains some scene, some sun, and a tree, and something else. If I would like to process this image, the processing will involve convolutional layers. So I can say that this image I can analyze using a set of filters. And if I have there will be many filters. Let's say I will have a filter that is H1. H1 is an array. Let's say this is a 3x3 array. So like this one. And it has some particular values. So a result of filtering of this input image will be some array that is of size. So this will be an output y, which is a result of convolving x with a blue filter. And then I will have a green filter. So this will be let's assume all these filters will have the same size, but the values obviously will be different. So a result of filtering will be another output, which will be a green output. And then I will have a red filter, a red filter, so the result of filtering will be just a red uh, array of red values, and so forth. I might have several filters, so that there will be some last filter, black one, and the application of this whole stack of filters, blue filter and green filter and red filter and more, to the X, application of these filters uh, to input image will produce an a kind of a three-dimensional array of outputs. And we will be talking about what comes next during our next lecture. But I will just to conclude, I will name this part as a convolutional layer. And the convolutional layer is actually a set of filters that transform input to output. And each layer, each filter, basically is just a set of neurons that are arranged in a 2x2 grid with appropriate weights. So each of these neurons, each of them has exactly the same set of weights, and this is just a blue filter. And there will be another set of neurons with different weights, and they will constitute a green filter. And there will be a red filter and many other filters. So this will be a green filter, and there will be more and more filters. And basically data processing will be just like in a neural network. You will be performing dot products of input information with neurons of the first filter. You will compute the output. You will again compute a result of a dot product with input and green filters. You compute the output, and you stack all these outputs into such a three-dimensional structure. And this is a result of the first stage of processing. And a network that I am introducing is just called the convolutional neural network. And we are at the beginning of this network, but we know an important thing right now, that convolutions are a way of extracting information. So the part that is responsible for extracting information, this part of this network will involve convolutions, and I can learn a filter because this fits the same framework as training of a regular multiple layer perceptron. This fits under this error backpropagation concept. So for today, that's everything that I wanted to tell you. And we will continue in a week from now. Okay. There are some questions related to the test. Could you could you, if you have just 4 and you would like to have 5, I would recommend you to take this test. So this is an answer to Mikołaj. I will send invitation to all of you. So that's the answer to the second question.